Okay, I'm Mehryar Mohri, and this is joint work with Anqi and Yutao Zhong, who are PhD students at the Courant Institute. And well, they could not show up to present this talk because due to visa issues. So I'm lucky that I get to actually present this work. So the title is Enhanced H Consistency Bounds. The H really stands for the hypothesis set. And even just starting from the title, you can see this is going to be a little bit technical. So I'll try to just give the main summary of the results. Let me start with the motivation for this work. Most learning algorithms resort to a surrogate loss. This is either because the original target loss, such as the binary 0-1 loss, is computationally intractable, or because the loss function is not differentiable, or it's not smooth, or in general not favorable for optimization algorithms. And so you're all familiar, let's say, in binary classification with some standard loss functions adopted for different algorithms, the hinge loss, logistic loss, exponential loss. These are all surrogate losses in the binary case. In the multi-class classification case, you have multinomial logistic loss, the so-called sum of exponential losses, or more generally, a family of loss functions referred to as the composition sum losses. So there are many surrogate losses. And of course, the main question, and probably a fundamental question, is which surrogate loss should one adopt? And even more importantly, in a way, what guarantee on the target loss can you count on when you're minimizing the surrogate loss? Whenever you ask such questions, a standard criterion or property that is brought up is that of the so-called Bayes consistency. What does the Bayes consistency say? It says that if you have a sequence of predictors, H sub n, and if you manage to find such a sequence such that the difference of the expected surrogate loss, for me, L tilde, that will be the surrogate loss of H sub n, minus the best surrogate loss you can find. In other words, the one for even the family of all measurable functions. H sub all, for me, will be the family of all measurable functions. If you can find such a sequence such that this difference tends to 0 as n increases, you would want the same property then to hold for the target loss. Okay? So it's, of course, a statistically nice property. It has been shown, I think, first by Tong Zhang, then later in a series of papers, including Bartlett et al., for binary classification, that many margin-based loss functions have this property. Tewari and Bartlett have shown something similar for some multi-class classification loss functions. And we have actually shown similar guarantees for other loss functions as well recently. But this property is only asymptotic. I think you heard Nikita yesterday. We don't really care about this sort of things, asymptotic guarantees in machine learning, because you would have to deal with like finite samples for one thing. And asymptotic guarantees do not tell you how slow the convergence rate would be. So this is already an issue, but perhaps an even more fundamental issue is that this property only holds for the family of all measurable functions. And of course, no learning algorithm is working with the family of all measurable functions. It's even worse because, in fact, Bayes consistency does not translate into better performance. In fact, you can show, and Long and Servideo have done this both theoretically and empirically, that if you, for some hypothesis sets, if you minimize a Bayes consistent loss, you would end up always with at least a constant error in some cases, while actually for the same hypothesis set, if you minimize an inconsistent loss, you can actually get the error to be 0 eventually. So this sort of tells you immediately that the hypothesis set, the role of the hypothesis set is crucial here. And of course, this is completely ignored in that definition. The question it brings up is, can we actually give hypothesis set specific guarantees that would be also non-asymptotic for surrogate losses? Okay? And that is actually what I'm going to present to you. But to do it, I first have to introduce a notion that we have referred to as the minimizability gap. So let me just take the time and define this because I'm sure it's going to be new to many. So given a loss function L and a hypothesis set H, the minimizability gap is, just depends on both the loss function and the hypothesis set. And it is defined as the best-in-class expected loss, that E star sub L of H, minus the expected pointwise infimum of the loss function. For that infimum is over the hypothesis set. Okay? All right? So it's not hard to show that this quantity is always non-negative. And additionally, it's always upper bounded by the so-called approximation error or the approximation loss. So it's a finer quantity than the approximation loss. That's easy to see because if you just replace H by H sub all, you just exactly find the definition of the approximation error. Okay. More interestingly, or perhaps another property, is that for pointwise loss functions, and most loss functions that you consider in classification are pointwise loss functions. By that, I mean a loss function such that the value only depends on h of x and y. Okay? For such cases, you can actually show that the minimizability gap is 0, for example, for the family of all measurable functions. This actually this requires like a measure theory kind of a lemma. Okay. All right. So this is a finer quantity. It's non-negative, and that's what's going to enter the guarantees that I'm going to present. So in the last few years, we have been suggesting for a family of surrogate losses, what we have been referring to as being H consistency bounds. So as the name indicates, there are hypothesis set specific, but they're also like non-asymptotic. So let me try to describe what they consist of. They are based on a increasing and concave function gamma. And they have the following form. Just look at the first line. It's a guarantee that holds for all predictors H in the hypothesis set. For a second, think that the two minimizability gaps, the one on the left-hand side and the one on the right, are both just 0, to simplify. And that's actually the case in realizable cases. In that case, what it means is that if you have such a guarantee, and if you manage to minimize the surrogate estimation loss, the difference of those two terms on the right-hand side, to, say, epsilon, then this guarantees that the true target estimation loss is bounded by gamma of epsilon. Okay? And now, of course, it becomes more general when you have the minimizability gap on both sides. So now it applies in a broader kind of cases. Since the function gamma is concave and defined over non-negative numbers, it is always subadditive. So, therefore, the right-hand side can be upper bounded by gamma of that surrogate estimation loss plus gamma of the surrogate minimizability gap. Okay? And so, of course, I would have to just repeat, if you manage to minimize, and that's what an optimization algorithm would seek to do. If you try to minimize or reduce the surrogate estimation loss to epsilon, then this is basically the guarantee that you would have, right? On the right-hand side, you would have gamma of epsilon. Think, for example, it's typically either a square root of epsilon or just epsilon itself, plus this quantity that depends on the minimizability gaps. I'm not going to insist on this a lot more. I want to draw your attention to the fact that these minimizability gaps actually play a crucial role. These bounds are actually for a fixed, if you choose the best gamma function for the hypothesis set, they're the tightest possible guarantees of this kind that would relate the surrogate estimation loss and the target estimation loss. And we have proven that under very mild assumptions, these minimizability gap terms have to show up. Okay? So here's an example for, actually, I think it's here for binary classification, but I think it's also something similar is true for multi-class. The gamma function in this case is the inverse of the familiar function for some, at least, that you can see here. And you can see the gamma function has the following shape, which probably reminds you of what? Probably like entropy. Well, because that form, but I'm just talking about this plot. I mean, so it looks like this square root plot, and in fact, near zero, the behavior is actually exactly the same as the behavior of the square root function. Okay, so this sort of tells you, what I was talking about, the square root of epsilon. This is what you have in the logistic loss case. Okay, and in fact, there's a discrepancy between what I see here and what I see here. Oh no, now it showed up. Okay, was that just me or it? Okay. So in recent work, we have actually shown what we refer to as a universal property for surrogate loss functions, which is that for smooth loss functions, think of virtually every surrogate loss function that people are using in practice for, I don't know, training neural networks or other hypothesis sets, and both in binary classification and multi-class, the behavior of this gamma function, and by that I mean the best gamma function. And the best gamma function you can find for that hypothesis set is really actually of the form square root of t. Okay, so that actually tells you something fundamental about surrogate losses in that case. But while that is a very general result, you still want to ask if one can improve on these guarantees, right? And how can we improve on these guarantees? In a way, I told you that if you fix the function gamma, and you look for the best one, this is the best, but that's the best for that kind of form of guarantees, where you have precisely been assuming a gamma function that is constant. So we have been considering what we refer to as an enhanced H consistency bounds which have the following additional ingredient in them, where it's similar to what I showed you before, modulo the fact that there is a little gamma of h. So there's a term that actually depends on the particular predictor h that can be included in the bound as a factor. Okay? And turns out that one can actually show, one can actually prove such, give such enhanced H consistency bounds, and that they can lead to, in some instances, both to better guarantees and actually to interesting insights in some cases. So I'm going to illustrate this in two simple cases. The case of multi-class classification in a low noise regime, and also for bipartite ranking. You know, much of what I said actually, in a way, it can be extended to that. Okay, so that's, I didn't realize that I was going so slowly, but that's okay because that's essentially the main message. There's a general tool that we are deriving for giving such bounds, and modulo the assumptions, this tool, or the guarantees, are actually tight. I am not going to discuss too much the familiar Tsubakov noise, but you know that Tsubakov noise assumption is typically for the binary case. It can be extended to the multi-class case. Essentially, it's telling you that the probability of low margin is small. And what we showed is that using these enhanced guarantees, you can derive what you could think of as being fast rate H consistency bounds. In other words, while you had, for example, in the logistic loss case, something that was of the form square root of t, that square root function can actually be between linear, say in the Massar's noise case, and the square root case, depending on how favorable the Tsubakov noise is. You know, some examples of the kind of guarantees that we show. And I'm probably going to just conclude on this slide, which relates to bipartite ranking. Several years ago, my colleagues and I, we were trying to derive an algorithm for ranking, for bipartite ranking. Turns out at the time, I was at Bell Labs, but I didn't actually realize that a colleague next to me, Rob Shapiro and Yutao Freund, they had actually also worked on the same. So we derived something that was basically like the rank boost algorithm. They had done it already. But it turns out then that we wanted to see how well it was behaving, and we ran experiments, and we compared with AdaBoost to just show that it would be doing better. And we were very surprised, because what we realized is that while rank boost was beating many other algorithms, at the time, in fact, all ranking algorithms, the performance of AdaBoost was almost the same as rank boost, while AdaBoost was not even designed for ranking. Later on, we actually wrote a paper on this to sort of show why there is a connection between rank boost and AdaBoost. And here, with these kind of like H consistency bounds, improved ones, we could derive something that is actually stronger. And I'm just going to describe it for you here. On the right-hand side, this is the estimation loss of the exponential loss that AdaBoost is minimizing. Okay, so this relates, the right-hand side relates to AdaBoost, if you wish. The left-hand side is based on the loss function for rank boost. And what this means is that this term here is quite interesting. So first of all, it says that this convergence rate is linear. Okay, the rate of the bound is linear. But even more interestingly, you have a term here that depends on the predictor H, which is the form that I mentioned would be very favorable for this bounds. And it says that the better the loss, the smaller the loss of the predictor obtained by minimizing the ADA boost loss, the better the rate of this convergence. So this is remarkable, okay? So that's showing actually in a very strong way, and not in an asymptotic way, as we had proven before, that you can derive a very strong relationship between, for ADA boost, which is really a remarkable property of ADA boost. We've actually extended this to the logistic loss as well, but I'm going to stop here since we run out of time. Thank you.
One quick question.
There's one question, I don't know.
So I was thinking about this minimizability gap, and it's sort of some measure of like how the hypothesis kind of factor across or split across X. But could you give some insight into when that's small, basically is the question.
Well, so first of all, it's a good and important question. I want to actually emphasize for everyone here, because I view these terms as being crucial. So some straightforward cases where they're small. Of course, when the approximation error is small, then because they're upper bounded by that, they would be small as well. But these are typically finer quantities. So there are cases where they can be smaller, and yet the approximation error is not necessarily small. I would have to give you hypothesis set specific and loss function specific kind of answers here. And in fact, I don't know the answer for many other cases. For some loss functions, we have given some preliminary analysis trying to bound this. But of course, you can imagine like the minimizability gap is not something that you can estimate actually. So you can only give guarantees that, or analysis before having seen data in a way. But yes, so all I can tell you as a broad intuition is that it's smaller than the approximation loss. In some instances, you can bound it in terms of the upper bound on the loss function, but a function of that upper bound. But there's a lot more to say. Okay.
Yeah, thanks.
Thank you.
Thank you.